The authorities at this event assigned me some lecture titles, which I think are fine. The first one was, what was it, quantum gravity? Or
why is gravity so hard to quantize?
Why is gravity so hard to quantize, or something like that? I would say it's not hard, it's impossible. I think there are a number of reasons why it's hard. The first is that it's a new range of parameters. It's something different. It's something we had no experience with before. And as always, when you come to a totally new experience, you better start by forgetting the things you need to forget. That doesn't mean forget everything. There are things that you learned in the past, let's call the past the 20th century, or at least the first 3 quarters of the 20th century, and those things prejudice you. They build up a set of expectations about how you do things, and those expectations, when you come to the next level, to the next range of parameters, to the next step, are often the wrong things. So there's always a period during which not just individuals, but the collective wisdom of the subject goes on a trip of forgetting, learning how to forget the wrong lessons. I think we're getting close to having eliminated most of the wrong lessons about quantizing gravity, but I think we're still fairly far from having a comprehensive description. And so what I'm going to tell you is a little bit, in particular, about where the new directions are coming from. The new directions are coming from some odd places. Well, you know what, I think I'm going to start. I think I'm going to start by not telling you about 20th century or 21st century, but I think I'm going to go back to the last day, literally, almost, of the 19th century, or maybe it was the first day of the 20th century, when Max Planck wrote what may have been the single most important paper in quantum gravity. This was before there was quantum mechanics, it was before there was general relativity, and Max Planck had just discovered the Planck constant, and he had a deep insight. The deep insight had to do with nothing more interesting than choice of units. Planck realized that there were special choices of units, and those special choices of units were based on the 3 most important, most fundamental, most general constants of nature. Let me first of all tell you what those 3 constants are. You know what they are. But let me tell you what I mean by saying that they are very general. They're not, for example, like the ratio of the mass of the proton to the electron. The mass of the proton to the electron is very special. Nothing general about it. It's got to do with the electron and the proton. It doesn't have to do with the Higgs boson, doesn't have to do with neutrinos. It's very special. When I say that a certain constant of nature has great general importance, I mean that when you go to describe what its importance is, you find yourself over and over saying, for every, or in all cases, or most generally under any circumstances, and so forth. The 3 quantities, and I'm going to get another one in a moment, the 3 quantities which have that character to them are the speed of light, Newton's gravitational constant, and Planck's constant. Right? So first of all, the speed of light. What does the speed of light tell you? It tells you that every object in the universe, it's just every signal in the universe, every physical method of communicating in the universe by sending energy back and forth can never signal faster than the speed of light. Notice that I didn't say that light goes with the speed of light. I said for every possible way that you can send signals. So that has great general importance. What about Planck's constant? Planck's constant, of course, is associated with the uncertainty principle. For every object in the universe, the uncertainty in its position times the uncertainty in its momentum is greater than or equal to Planck's constant. Again, the use of the word every and for all and so forth. Finally, there's Newton's constant. Newton's constant says that for every pair of objects in the universe, no matter what they are, that there's a gravitational force between them which is proportional to the product of their masses, inversely proportional to their distance squared, and proportional to Newton's constant. So those three constants of nature, and it was Planck who really realized this. He realized that they were very, very general. They had to do with almost everything you could think about. And therefore he said, why don't we invent units based on those three constants, units in which those three constants are set equal to 1. He didn't really know why. He didn't really know what importance that would have. He certainly didn't have any inkling of what would be going on today with these constants and so forth, or with these units, but it was deep insight. So let's just talk about those units for a minute. Given the three quantities, C, can that be read? Everybody read that one? C, H bar, G, you can build a quantity with units of length. Better yet, because I like to avoid square roots, you can build a quantity of area. Length times length. It's called the Planck area, and I'll write it L Planck squared. It's given by G, H bar, divided by C cubed. It's a very small distance. G is very small, H bar is very small, and C is very large. So this is a very small unit, but when I say it's a small unit, in what units am I saying it's a small unit? In its own units, it's just one. It's small in human units. It's small in units in which humans daily do things. But for a physicist, there's no reason to be using the length of a man's arm to discuss microscopic physics. And so a physicist who's interested in quantum gravity doesn't think of it as small. He thinks of it as the unit, the basic unit. The unit means one. That's the Planck unit, Planck length. There's a Planck time, and the Planck time is simply the time that it takes light to go 1 Planck distance. Oh, this incidentally is about 10 to the minus 70 meters squared. This is beginning to show you immediately why quantum gravity is so hard. It's because it's about extremely remote things. Things whose distance scales, time scales, are extremely remote and about which we know almost nothing. At least we know nothing from experiment. TP, that's L Planck, same L Planck, divided by the speed of light. And that's about 10 to the minus 43 seconds. Just for those of you who may not be used to dealing with particle physics and so forth, these numbers are vastly, vastly smaller than any numbers that come up in experimental physics. Even the biggest accelerators, they're miles and miles and miles away from the sorts of things which we normally probe. Finally, there's the Planck mass. The three constants are used to define three units: length, time, and mass. And Planck mass, now you might from these numbers expect maybe the Planck mass is some tiny, tiny, tiny mass, much smaller than anything, but that's not right. The Planck mass is unusually large. Not large in units of pounds, not pounds, but kilograms and so forth, but very large in the units of microscopic physics, elementary particle physics. In fact, it is a microscopic mass in a sense which I'll tell you in a minute. Well, if you wanted to see, it's about the mass of a dust mote, a little bit of dust, and it's about 10 to the minus 7 kilograms. Is that a big mass or a small mass? Well, it's nothing in smallness compared to an electron or a proton. It's much, much bigger than that. But another way to describe it is to use E equals mc squared and ask how much energy that it corresponds to. The answer is, with about 10 Planck masses, you could drive across the country. It's about a tank full of gas. You explode a tank full of gas, it's about the same energy as 1 Planck mass. So it's pretty microscopic, it's pretty macroscopic. The last constant I want to introduce is often not thought to be that fundamental, but it is. It is very fundamental. It's called Boltzmann's constant. How many people do you know Boltzmann's constant? Good. Okay? What, if I ask you if you know what Boltzmann's constant is, you probably might know, I don't know, but I probably wouldn't quite have the same answer I have. You might or you might not. All right, the next one is K. Boltzmann. K. Boltzmann is of order 10 to the minus 23, I don't remember in some units or other. But K. Boltzmann is really, it's also very general. But it's a conversion factor. Yes?
A quick question. So up until now, what we did is we took certain fundamental constants of nature and we combined them to give us length, time. But is it so straightforward immediately that this must be where quantum gravity is working? Like, how does that follow?
It doesn't. It doesn't. It doesn't. It was a guess. It was a good guess. I mean, we have to understand more about quantum gravity. But, you know, if you want to know what the scale of the phenomena are that have to do with quantum mechanics and gravity combined, this is what you might do first. This is the thing you might do first. You might ask what are the length, time, and mass scales that correspond basically to setting these three constants equal to 1. Using the Planck length, the Planck time, and the Planck mass as your units automatically sets these nasty, unpleasant constants which appear all over in your equations and sets them to 1. So it's a guess that these are the important things. Now, by now we know a great deal more, and we'll talk about the meaning of these, but let's just take as a guess. Okay, K. Boltzmann. What is K. Boltzmann about? K. Boltzmann has nothing to do with gravity, has nothing to do with quantum mechanics. It has to do with heat, molecules, and that sort of thing. But it's really a conversion factor. It's a conversion factor. Temperature, the basic thing of temperature is that it's energy. It's roughly speaking the kinetic energy of a single molecule in a gas or a liquid or whatever, and its natural units are energy. But when people first started measuring temperature, they measured it with with a device. They had no idea what it was they were measuring. They didn't know what they were measuring was the kinetic energy of molecules. And so they invented units, Fahrenheit, centigrade, Celsius, or whatever. And those units were just the units of thermometers that they invented. But with Boltzmann's discoveries, and also Maxwell, it was realized that temperature is a form of energy, and that the units for temperature ought to be units of energy. K. Boltzmann is the conversion factor that takes you from, let's say, centigrade units or degrees Kelvin, takes you from temperature to energy. Once you know that temperature is a kind of energy, you can get rid of Boltzmann's constant, but it's a good thing to remember. But it's also another kind of conversion factor. It's a conversion factor between entropy and information. What is information? I'm not going to be tremendously precise about what it is, but I'm just going to say it's the number of bits, yes-no questions, that you would have to ask of a system to know its precise state. You can always reduce questions to yes-no questions if you're willing to ask enough yes-no questions. And you can always reduce the question to the minimum number of yes-no questions that you have to answer in order to know the state of the system. And information is basically just the minimum number of yes-no questions, plus minus ones, bits. It's measured in bits. Information is measured in bits. In quantum mechanics, it's measured in qubits, quantum bits. But the Boltzmann constant is the conversion factor from entropy to number of bits of information. Maybe I should just say a word or two more about entropy. Entropy is a kind of information. It's typically hidden information. If you have box of gas or a container of fluid, a bathtub full of water. How much information do you need to know whether to take a bath in the water? Basically, you need to know its temperature, you need to know the volume of water to make sure that you can fit into it, and you need to know a couple of other things. Maybe you want to know the chemical composition of the water, you want to know it's not hydrochloric acid, but a handful of pieces of information. That's all. In other words, the thermodynamic information, the coarse-grained information. But there's lots more information in that water if you wanted to know its precise, exact state, namely the position and velocity of every single molecule. That's classical, or in quantum mechanics, the precise quantum state of the whole system. That's a huge amount of information, but it's hidden. It's hidden because the number of degrees of freedom is too large, they're too small, and they're too difficult to keep track of. So all of that information is called entropy. And you can think of it, as I said, as the number of yes-no questions that it would take to precisely describe exactly the state of whatever it is you're talking about. Entropy and information, and the conversion factor is K. Boltzmann. One other thing about these quantities, it is believed that they have a lot to do with black holes. So I'll just tell you quickly, we're going to come to black holes, but for the moment, the Planck mass is believed to be the mass of the smallest black hole. And you say, where did that come from? Well, we're going to find out where it comes from. We're going to find out that a black hole which weighs less than Planck mass has less than 1 bit of information in it, and you can't have less than 1 bit of information, but we'll come to that. The Planck time is the lifetime of such a black hole. How long it would take for it to evaporate instantly into radiation. And the Planck length is basically, or the Planck area, is the area of the horizon of such a black hole. So it is believed that these 3 units here are connected with the smallest possible black hole. So we'll come to that. Okay. Given that we know so little, and everything is so terribly remote, that our chances of ever having experiments about quantum gravity are extremely remote, what is the possible doorway in which a sensible theoretical physicist will try to get into this room of quantum gravity? Where might there be an entry? Well, the first hope for an entry was to treat quantum gravity the same way as quantum electrodynamics, to take Einstein's equations and to quantize them. What does it mean to quantize them? There was a set of rules that were laid down by Dirac, an alternative set of rules that were laid down by Feynman, closely related, of course, for taking a classical system, a basically classical system, and quantizing it. If you know a little bit about quantum mechanics, you know what the rule is. The rule is you replace Poisson brackets by commutators, or in Feynman's point of view, you take a classical action and you take it as a thing that you sum over to find amplitudes by the method of path integrals. But what you're doing in every case is taking a known classical system which had nothing to do with quantum mechanics. The system was perfectly sensible by itself, and superimposing on it, because of experiment, not for willy-nilly reasons, but because of experiment, superimposing on it the structure of quantum mechanics, but with no really deep connection that were telling you that if I gave you this equation, Maxwell's equations is an example. Maxwell's equations is quantized, the result is quantum electrodynamics. The orbits of a particle moving in a central force field, in a 1 over r squared central force field, you can also quantize that. It becomes the Bohr atom and so forth. Or the Schrodinger version of the Bohr atom, Schrodinger-Heisenberg version of it. But they are classical systems which you then just take and quantize them. So the first natural reaction was to try to quantize Einstein's equation. It was a dismal failure. The worst part of it had to do with its inability to understand what was going on in black holes. That was the worst part of it. But there were all sorts of things leading up to it. Everything that you calculated in perturbation theory was infinite. Nothing really quite seemed to make sense. And on top of everything else, black holes had no place in that description at all. As we've moved on, we're beginning to understand that, that quantum gravity is a much more intricate collection of ideas in which if you take any one of them and try to remove it, you probably disrupt the whole thing. You can't separate it into classical and quantum mechanical. It's intrinsically quantum mechanical. You can't take it and think of it as just gravitational field equations. Not good enough. So there are four, in particular, there are four things that have come together, four basically separate disciplines that have come together, and now, over the last 10 years or so, are beginning to form some sort of focus where we begin to see some new ideas. I'll tell you what those four things are. Of course, they are quantum mechanics. They are gravity in the form of Einstein. That would make quantum gravity. But they're thermodynamics. What does that have to do with quantizing gravity? Well, we'll find out what it has to do with quantizing gravity. And information theory. Quantum information theory specifically, quantum information, or information theory more generally. Information theory was a thing that was discovered in the 1940s by Claude Shannon, how to quantify the concepts of information, advanced by people like von Neumann, who constructed quantum information theory. And the key notion in quantum information theory, anybody know what the key notion in quantum information theory is?
Entanglement.
You betcha. Entanglement. Maybe I should have put entanglement up on the top. I think I should have. But all of these things are leading to a picture of quantum gravity which is much richer and far more interesting than just quantizing Einstein's equations. So I'm going to tell you a little bit about these different directions, why I draw this picture here, and what it has to do with. Incidentally, Kate Boltzmann, of course, has to do with the relation between thermal and information. That's why I left it up there. Okay, so let me begin with one of the ideas that we have to forget. It's the basic history of 20th century physics, essentially, or 20th century microphysics, 20th century quantum mechanics and quantum field theory. It's the basic idea that small is the same as heavy. Heavy means energetic, E equals mc squared. So when I say heavy, I mean lots of energy. The smaller a thing is, the more energy it has. The more energy that's concentrated on a single particle, the smaller its wavelength, for example. A manifestation of that is the fact that the energy of a particle associated with a wave of wavelength lambda is given by h bar c divided by lambda. Now, I can never remember. There's a 2 pi in there. Is it the numerator or the denominator? Nobody else knows. Good. Forget it. I think it's the numerator. No. Yeah, the numerator. The energy of a particle with a given wavelength, in other words, the energy associated with quanta of fields moving with a certain wavelength, grows as the wavelength gets smaller and
So
smaller.
Lenny, it's 2 pi in the numerator. It's just hc over lambda.
You're
H
right.
nu.
It's 8, that's right, it's hc over lambda.
H nu.
It's
nu.
the same,
Right.
it's all the same.
Planck formula.
Right. That's right. When we were graduate students, we used to have a joke. We'd come up and say, what's new? Oh, E over H.
Only works in New York.
Okay. Now this connection was completely central to 20th century physics, experimental physics, theoretical physics. And for example, it is what led to the requirement of building large accelerators to see small things. If you want to see the really small substructure of a thing, here it is. How do you do it? You use a wave. And the wave has to have a wavelength that can resolve the small structure. So if the structure is small, you need a small wavelength, and that means you need large energy, and so you build a big accelerator. That's, if you like, 20th century physics in a nutshell. Okay? We could plot it. We could make a plot, a drawing of what this means. I want to plot vertically the resolving power, or resolution. Resolution means how small an object can you see. I'll plot vertically the length scale that can be studied for L resolution versus the energy, for example, of a beam of particles. But this is much more general than that. Specifically, it could correspond to the beam of particles that can be studied LR, but we know what it looks like. It looks like a parabola and folds up like this. As I said, that is 20th century microscopic physics. In a simple, it's probably the most single important link between theory and experiment in 20th century physics. Okay, now let's try to push on this and see where it goes. I would like to use the same idea to build myself an accelerator which can find out what's going on distance scales smaller than the Planck length. Mr. Planck told me that there's a fundamental length called the Planck length. It must have some special meaning. So what I want to do is build an accelerator in a beam of particles that will explore what's going on at a distance scale of 1/1000th of a Planck length. What do? Well, I build myself an accelerator that can accelerate particles to 1,000,000,000 times the Planck energy. 1,000,000,000 times the Planck energy will have a wavelength 1/1000th of a Planck length, and I do the same kind of experiment. Well, before I do that, let me just remind you what an ordinary experiment looks like. If you want to see quarks inside a nucleus, you'll do the dumbest thing possible. You scatter two, not nucleus, but inside a proton, you scatter two protons together. If the energy is high enough, you have enough resolution power to see the small distances, and out go flying quarks. And those quarks go flying out with energies comparable to the collision energy, and you see them one at a time. And that's using your resolving power to explore what quarks are like. We want to do the same thing to find out what's going on at distances much smaller than the Planck scale. So we're going to collide two particles together at energies of 1,000,000,000, 10 to the 9th, and Planck. Don't ask where we're going to get those particles from. It'll be a while until we build an accelerator that can do this. It would take an accelerator probably a good fraction of the whole size of the universe to do this. But I don't think there's anything in the laws of physics which say that it can't be done. So let's imagine it was done. We collide these physical particles together. We ask where it comes out. You might say, how are we ever going to, we'll never know what comes out. You can't do that experiment, and it's so far and so remote from us that we have no idea, and we never will have any idea. That's probably wrong. We probably know exactly, yes, we probably know exactly what comes out. When you take that much energy, and you compress it into a small volume, such as what you would get when you fire two particles together, we think we know exactly what happens. We think a black hole forms. A black hole forms. Let's write down the basic equation of black hole physics, which tells us how big that black hole is. Here's the equation. The size of the black hole, the Schwarzschild radius of the black hole, which we will come to, the Schwarzschild radius of the black hole And it's basically a measure of the size of the horizon of the black hole. The size of the horizon of the black hole is twice the mass of the black hole, Newton's constant, divided by the square of the speed of light. Newton's constant is a small number. The square of the speed of light is a big number. So typically the Schwarzschild radius is a very small number for ordinary masses. For example, for a mass of the Earth, the Schwarzschild radius would be about as big as a peanut. The mass of the Sun comes out to be about a kilometer. So a black hole is very small for its mass, but 10 to the 9th Planck masses would give you a black hole which would be 10 to the 9th Planck lengths. Very small by human standards, but rather large by the standards of these basic numbers here. And as we will see, not only do we know that a black hole will form, notice that the black hole gets bigger and bigger as the mass gets larger and larger. In other words, as the energy pumped in here gets larger and larger, instead of seeing something smaller and smaller, whatever goes on here is shrouded inside a black hole. We can't see it, and all we can see is the growing size of the black hole. But what comes out? What really comes out? What comes out is Hawking radiation, which we're going to talk about. Radiation, thermal, good old photons, but the photons themselves have a wavelength that's about as big as the Schwarzschild radius. So what's the upshot? The upshot is by trying to pump more and more energy in there, larger and larger energy, to see smaller and smaller things. Instead of seeing smaller and smaller things, we see bigger and bigger. Bigger and bigger black holes, longer and longer wavelengths. In other words, we just reproduce what we already knew from large-scale physics earlier. Now we may discover some new things in that radiation, but they won't have to do with smaller and smaller distances. So the upshot is that in the 21st century, as we think more and more about quantum gravity, this curve is going to bottom out and grow. As the energies get larger and larger, instead of seeing more and more small things, smaller and smaller things, we will see larger and larger things. However, we will still be seeing a new frontier. It will be a frontier of complexity, information, entanglement, and new structures that we have never thought about before, having to do with larger and larger things. All right, so the first, my point now is one thing we have to forget is the basic lesson of 20th century physics that small equals energetic, and probing small distances means using high energy. That has to be forgotten. And quite the opposite, once you get past this transient initial behavior, as the energy goes up and up and up, we'll be seeing bigger things. Now that's a guess, of course. I mean, nobody can say for sure what anybody's going to see when such a machine is built. But on the other hand, I don't know anybody who doesn't more or less agree with this picture. That doesn't mean it's right. Okay, as I said, I asked somebody what the fifth link on that wheel was that I had up there, and they said entanglement, and they were exactly right. We're living now as theoretical physicists in the age of entanglement. If you go to the archive, the physics archive, and you look up high energy theory, not accelerator-based high energy theory, but string theory, black hole physics, all the theoretical things that modern high energy physicists think about, even cosmology, and condensed matter physics, solid state physics, you'll find every single day several papers with the word entanglement in the title. Something is happening, a revolution of some sort is happening, and it's happening about the concept of entanglement. Entanglement, incidentally, Einstein is just a guy who just keeps giving. He just never lets go. He just keeps giving. Entanglement was probably Einstein's last big contribution to physics. Famous paper. How many people have heard of EPR? Einstein, Podolsky, and Rosen. Einstein, Podolsky, and Rosen was the first paper that put their finger on the concept of entanglement. It drove Einstein crazy. He didn't like it. He thought it was saying something very, very strange about reality. Bohr told him, Bohr's argument was very simple. Bohr said, take an aspirin, you'll feel better about it in the morning. It's a consequence of quantum mechanics, that's just the way it is. Too bad, Albert, you've got to accept it. Einstein never accepted it, and it was when historians think about Einstein's failure to be able to come to grips with quantum mechanics, it had to do with that. My own view, and I think more and more, my colleagues have the sense that although Einstein may have been technically wrong about, well, he never said that quantum mechanics was wrong. I think morally he will be the victor. In the end, the strangeness and peculiarity of entanglement will, I really believe, will be the great lesson that was learned from the Bohr-Einstein debates, and not Bohr's simply shoving it aside and saying, too bad, that's a consequence of
I think even, I mean, I think you don't even go far enough in,
maybe you don't.
because Bohr showed no appreciation to what Einstein had in mind. Einstein was wrong, of course, but he was much
Well,
closer.
I don't know that he was wrong.
No, he made it, there were things which were definitely wrong, but Bohr had no clue.
Bohr had no clue. That's correct. Bohr had no clue. Now, I have to say, when I first heard about entanglement, it was so obvious to me, as it was probably to Bohr, it was so obvious that it was right and that it was a feature of quantum mechanics that I myself said, oh, this is not so interesting. It's a feature of quantum mechanics, yes. Over the last 50 years of thinking about it, it has been 50 years, I have really come to appreciate that this is the central essence and the central essence of quantum mechanics, and more than that, I believe it's going to be the central ingredient in our understanding of gravity. I'm not alone in that view, incidentally, not at all. Okay, so how many people here are experts at entanglement? How many people are a little bit experts at entanglement? How many people know nothing about it? I don't know where that puts me. I have no idea where to go from here. Okay, I'm going to talk about entanglement. We're going to learn about entanglement. Entanglement has to do with what happens in quantum mechanics when you combine systems, each one of which you know everything about, you know how to do its quantum mechanics, and you want to combine them into a combined system. You want to make a system out of two systems. What are the rules? So I'm not going to spend a lot of time formalizing it. I'm just going to tell you roughly what the rules are, and then we're going to explore the concept of entanglement. So we have two systems. One is called one of them is called B. As always in quantum mechanics, and especially in quantum information theory, A will stand for Alice, and B will stand for Bob. And we'll talk about this as Alice's system and Bob's system. I may forget, let me just call it A and B, but when I do start thinking about Alice and Bob, it will be this A and B. Sometimes there's a third system, and the third system, of course, is Charlie. I see. We may introduce Charlie. All right, so we have two systems. These two systems could just be different regions of space. They could be nothing more complicated than different regions of space. And the question is, what kind of linkages can we imagine between these things? For example, supposing they were just these regions of space. What links them? What relates them? There are questions you could ask, for example. Why don't they just fall apart and disintegrate into non-regions and fly apart from each other? Well, it's a little hard to imagine space just disintegrating and falling apart. We can ask how far apart they are. What we're beginning to learn again is that the answers to these questions have to do, in classical relativity, we just say there's a metric. There's a metric tensor, and the metric tensor tells us how far apart they are. In the quantum theory of gravity, it appears that that is closely connected to how entangled they are. The more entangled they are, the closer they are. The less entangled they are, the further they are. The more entangled they are, the more resistant they are against falling apart. What does falling apart mean? Well, gravity allows geometry to do very strange things, and even allows regions of space which look like they're close together to disintegrate. So entanglement is important in our understanding of how spatial regions fit together to form bigger regions of space. But for the moment, let's just think of these as two abstract systems. They may or may not be regions of space. They may be just two electrons. They may be just two spins of electrons. Could be anything, and we'll call them A and B. How do we describe them quantum mechanically? Well, let's suppose we have a description of A, and A is described by a complete set of commuting observables. Everybody know that term? I don't know if you know it or not, but it means everything you need to know about the system. A complete set of commuting variables labeled by A, and there are ket vectors. I know that you've learned about ket vectors because I've heard that you've learned about ket vectors, am I right? Okay, I will assume you know it. That there are a collection of ket vectors which describe the states of A, and they can be labeled by some basis of complete set of observables. Could be position, could be momentum, could be some spin degree of freedom, and that labels the A state, the states of A. What about B? B also has a description in terms of ket vectors. I'm not going to try to distinguish the A states from the B states by different curly-cued vectors. We just draw them the same way. But what about the combined system? The combined system is described by a tensor product of the space of the vectors which describe A and which describe B. In other words, we describe the combined system by a collection of states which are labeled by both A and B. That's easy. You describe the combined system by combining together the labels that describe A and B and put them into a single ket vector. And that's called the tensor product of two systems. What do you do with these basis vectors? You build more general vectors. So you build a sum over A and B. This is a generalization of what you would do for the single system. A wave function psi of A and B times the ket vector A and B. That's a general state of the combined system, and it's described by a wave function. A wave function is the amplitude that if you were to measure A and B, you would get the answer A and B. It's the amplitude. What do you do with an amplitude to get probabilities? You square it, multiply it by its complex conjugate. So these are the amplitudes. They correspond to wave. They're called wave functions, and they are the coefficients of the expansion of the combined system into some basis of
Ronnie, strictly speaking, what you had in the middle with the AB together,
yeah.
that's just a Cartesian product. The tensor product doesn't come until what's on top in the middle there.
Sorry?
The tensor product is the last thing you wrote down. Before that, it was just a Cartesian product.
I'm not sure.
Nothing. You have a state of A and a state of B, and if that's all you had, if you didn't form
Yeah.
that would just be a familiar situation, no entanglement.
Yeah. But if I call them vectors, it's implicit that I can add them.
Well,
No, you're right. You're right. But if I
yes.
once I prejudice by drawing it as a vector, it's implied that I can add it. But yes, that's right. This is the new ingredient in quantum mechanics, that you can take states and add them. Right. So, good point. All right. So now we come to the kind of states that you can have. Now, surely there must be states. If you can have some particular state of the A system, let's say characterized by a wave function phi of A. You get the B system. Suppose the B system weren't there. We might have a state of the A system characterized by just a wave function of the A degrees of freedom. And nothing special about it. Likewise for B. We might have a state which is characterized by a wave function chi of B. What about a state which is phi of A for A and chi of B for B? We just multiply them together to form a wave function, which is called a product wave function. A product wave function, if you were to do experiments on A, would have all the properties that you ascribe to phi of A. In other words, it's a state in which you know everything about the A system which can be known. It's described by a quantum state, phi of A, and B doesn't come into it. On the other hand, chi of B is a state of the B system which has nothing to do with the A system, and if you multiply them together, you get a combined state which has the properties of phi of A for A and chi of B for B. It's called a product state. But gee whiz, I mean, not all functions of A and B are products. Not all functions of A and B. It's like saying every function of x and y is some function of x times another function of y, and that's of course untrue. States like this are very special and rare, and not the generic situation. The generic situation is that psi of AB is not a product, and when it's not a product, that is when you have entanglement. Entanglement is a feature of wave functions for combined systems which do not form a product, and therefore for which you can say neither A nor B have their own distinct state. Only the combined system has a distinct state, and the subsystems A and B do not have states associated with them. Rather, the combined system has a definite wave function, and the individual systems don't. That's called entanglement. But still, even if we have an entangled state, supposing psi of AB is not a product, we still should be able to ask questions about A without looking at B. We still should be able to ask questions about A. It may be that the answers to the questions somehow depend on chi B, but nevertheless, we should be able to ask questions only about the system A by itself. How do we do that? It doesn't seem to have a state by itself. How do we do that? All right, the answer is the method of density matrices. Now again, I'm not sure how fast to go. How many people are familiar with the notion of a density matrix? Good, a fair fraction, so I'll go reasonably fast. But I'll tell you what the idea is. Supposing I have an observable, let's call it X. Now, observables in quantum mechanics are operators, Hermitian operators, and they can be thought of as matrices. Let's think of them as matrices. And this is an observable that's associated with the A subsystem. That means if we just had the A subsystem, it would have matrix elements with two indices, X of A prime and A. What would we do? Let's first think about what we would do to calculate the expectation value of X in a state psi of A. Let's suppose now we have a state characterized by psi of A. How would we calculate the expectation value? The answer is simple. Here it is right over here. We take psi star of A prime, X of A prime and A, psi of A, and we sum it over A and A prime. This is the same as psi x psi. That's the expectation value of X. And just look at its structure for a minute. It has an A prime that's summed over, it has an A that's summed over, and sandwiched between the psi's is X. All right, now, what about if we're talking about the combined system? If we're talking about the combined system, then whatever X is, it doesn't act on the states of the B system at all. It's just passive. The B system is completely passive. The operator X only acts on the A half of the subsystem. Technically, it would say that X, technically it would say that X has a delta B prime B in it. But basically, you can just think of it as being passive, doesn't do anything to the B indices at all. What then is the right answer for the expectation value if psi is drawn not from these single particle, not from these single subsystem states, but from the combined system? Well, the answer is pretty easy. You just write exactly the same thing, A prime A, psi of A, but you put in B as a kind of spectator. It just goes along for the ride. X does not make transitions between B and B prime. It does make transitions between A and A prime, and you sum it over everything. A prime exactly as before, but also B. You don't have to worry about B prime, because B prime is equal to B. This is the rule. It can be derived from other things. There are deep reasons why this is the rule, but let's just accept it as a rule. And now look at it, and notice the following. Supposing we don't want to think about B at all. We just want to think about A. Well, how does B come into this? It comes into something, but it's summed over. So let's take the object. If I'm going too fast, tell me. But let's take the object. Let's come over here. Psi star of A prime B, psi of AB, and sum it over B. That's what appears here. Summed over B, psi star of A prime and B, psi of A and B. Let's take that and do the sum. Do the sum over B. And give this object a name. The name for it is the density matrix. The density matrix of which subsystem? The density matrix of the A subsystem. It doesn't have any B indices. B is summed over. This is called rho of A prime and A. Oops, A prime and A. B has disappeared. We summed over it. This is some characterization of the state of A. It's not a standard quantum state. It's a mixed state. It's a pure state. It's a density matrix state. But it characterizes every question that we could ever ask about the A subsystem by itself. In particular, if we want the expectation value of X, we would now write it as expectation value of X is equal to rho A prime, I think it's A, let's see, it's A prime A, X A prime, summed over A and A prime. No more B's. B is gone out of the problem. We've, we would say you've integrated out B. B has disappeared by being summed over. If you know rho of A and A prime, then you know the expectation value of everything associated with subsystem A by itself. And so this is a valuable thing. If you know it, you don't have to refer to B if you're an experimenter who's doing an experiment on A. Now, of course, you can do exactly the same thing for B. Get rid of A out of the description. And those are two different density matrices, one for A and one for B. I should label them. This is the A density matrix, but I don't have to because its indices here are A indices. And you would do the same thing for B. Rho is a description of a composite system when it is not in a product state. In fact, it's perfectly good also if it's in a product state. And this object plays a leading role in quantum information. Okay, so let's explore it a little more and find out what we can about it. First of all, any questions? Are there any questions right now? Yeah.
Can there be more than two subsystems that are intact?
Yes. Yes. And the theory of entanglement of what are called tripartite systems is very complicated, much more complicated than bipartite systems. But yes, the answer is yes. have more complicated things with 3 subsystems, 4 subsystems, and it very quickly gets into a land of mathematical lack of knowledge, I would say. Okay, so here we have everything we know about subsystem A. What do we know about rho? All right, so I wrote down what rho was before. It's obtained by taking psi star psi and summing over B, but I'll tell you some of its mathematical properties that just follow from its definition. First of all, rho is such that its trace. Does everybody know what a trace is? Trace is 1. That's the sum of its diagonal elements. It is also the sum of its eigenvalues. The sum of the eigenvalues of the matrix is always equal to the sum if it's a Hermitian matrix. First of all, it's Hermitian. It can be diagonalized. It has eigenvalues. It has a complete set of eigenvalues. And those eigenvalues sum to 1. That's as a consequence of normalizing the wave function. Psi star psi summed over everything should be equal to 1. That tells you that the trace of rho is equal to 1. Another fact, all of its eigenvalues, let's call its eigenvalues P sub I, where I runs over a basis of states, runs over the eigenvalues of the matrix rho. How big a matrix is it? That depends on the size of the system A. If the Hilbert space describing A has dimension D, then there are D eigenvalues, see that? But these are all less than or equal to 1 and greater than or equal to 0. That also follows from... So it's called positive semi-definite. The trace of rho equals 1, that's the same thing as saying that the sum of the eigenvalues is equal to 1. And that basically makes P a probability. Probabilities lie between 0 and 1, and they sum to 1. P sub I can be thought of as the probability that the system lies in a state. What state? The eigenvector that goes with this eigenvalue. Now, what this is telling us is that there are 2 kinds of uncertainties in quantum mechanics when we look at a subsystem. There's first of all the usual uncertainty associated with quantum uncertainties even when you know the state of the system. But there's another kind of uncertainty that has to do with not knowing the state of the system. Not uncertainties which are implicit because the state of the system has some wave function which is spread, but implicit in the statement, I don't know what the wave function is with any reliability. These probabilities here are associated with the probabilities for different possible states of the system A. Once it's entangled with B, we don't even know if there's a definition of it having a state. The states that it has are probabilistic distributions of different possible states of the subsystem A. That's what happens when you have entanglement. You cannot, not only can you not say anything definite about measurements, you can't even say anything definite about the state of subsystem A because it's entangled with B, but you can ascribe probabilities to the different possible states of A. And to do that, let me just give you the recipe. You take the density matrix, you diagonalize it, you find the basis in which it's diagonal. The basis in which it's diagonal provides a set of states, and those set of states have probabilities which are the eigenvalues of the density matrix. That's the theory of density matrices in a nutshell. Now, what kind of density matrices, let's see what kind of density matrices you might be able to get. I'm going to tell you facts now. If the state is a product state, if psi is a product state, and you calculate the density matrix, and you calculate its eigenvalues, what you will find for product states. You calculate the eigenvalues of the density matrix for the A subsystem, you will find out that the eigenvalues are 1, 0, 0, 0, 0. In other words, you will find one eigenvalue equal to 1, and all the others are 0. This is another way of saying that a definite state, when it's a product state like this, A is in a definite state. There's no ambiguity about what the state is. It's just the eigenvector associated with the eigenvalue 1. All right, so the probabilities here, certainty for some state, and complete certainty that's not another state. That's the case for a product wave function, and that's not surprising, because for the product wave function, we do know that this is definite state for A. And this is just telling us this is a definite state for A. This, I would say, the product state is a state of what you might call maximal information. You can't have more information about A than just knowing its quantum state. It has a definite quantum state. Now, what's the opposite extreme? The opposite extreme is where the probabilities here are all equal. If the probabilities are all equal, it tells you you know nothing about the subsystem A. In other words, there's no information. So the other, this is called a maximally entangled state, and I'm going to show you some examples. Maximally entangled. A maximally entangled state has eigenvalues 1 over n, 1 over n. N is the dimensionality of the space. They've got to add up all together to 1. 1 over n, 1 over n, blah, blah, blah. In other words, every state equally probable. Another way to say it is that the density matrix itself is proportional to the unit matrix. All equal eigenvalues, the density matrix is proportional to the unit matrix. So let's write that down.
But I mean, there's even, I think what you're saying should be taken with a grain of salt, because
Say it again?
it should be taken with a grain of salt, because in this case we're talking about now, there's even more uncertainty, because there's nothing special about the particular basis.
Yeah. That's right. We'll come to that in a minute. That's exactly right. It's not a grain of salt. You're just adding another element to it. And it's a correct element. What's your name?
Shelley.
Shelley. Okay. Did I know you about 50 years ago?
Yeah, 50 years ago.
Thought so.
You have a good memory.
You know, Joel is one of my closest friends. Okay. I'm lost. Where was I?
What?
Remind me where I was.
Oh,
Shelley,
you
please
should
remind me
know.
where I was. I don't remember.
Maximally entangled state.
You said something important, but I can't remember what it was. Oh, I do remember. Sorry. In this situation, maximal entanglement and minimum amount of information about the system A, what you can say is the density matrix is proportional with a 1 over factor of n in front of it times the unit matrix, times the unit operator. Now, the thing about the unit operator is it's the same in every basis. That means not only don't we know which of several basis states the system is in, there's not even any preferred basis. The system, you lack all knowledge of anything about measurements on A in a maximally entangled state. In a maximally entangled state, A and B are entangled. You may know the AB system completely, meaning to say that you know its exact wave function. You know all there is to know about the system. There cannot be more. Once you know the wave function of the system, that's it. And yet you know absolutely nothing about A. The opposite extreme is the product state, where you know everything that can be known about A. Well, maximally entangled state is a state where you know nothing about A, and incidentally, in a typical situation, you also know nothing about B. What can it possibly mean to say that you know a great deal about the AB system? And we're going to find out that when a system is maximally entangled, you'll know nothing about A if you were to do experiments on A, you know nothing about B if you were to do experiments on B, but you know a huge amount of correlation. Measure something about A and it immediately tells you something about B. Measure something about B and immediately tells you something about A. I would go even further. When you have maximal entanglement, you can measure or you can find out the result of any experiment on B by doing an experiment on A. They are very tightly correlated. So it's a trade-off. Maximal entanglement, you know nothing about A and B separately, just random results of experiments if you were to do experiments, but you know a great deal of correlation between them. Product states, by contrast, you know everything about A if you were to do experiments on it, you know everything about B if you were to do experiments on it, but they are uncorrelated. They're product probability distributions, completely uncorrelated. Is there a question?
Yeah, I just wanted to check. Do you ever in a situation where, like, the reduced estimation for A takes the form of 1 over n times I, the reduced estimation should be doesn't take?
Sorry, very slow.
Oh, sorry. Do you ever in a situation where, I mean, I think the answer is no, but just check.
Slow, slow, slow.
Sorry. So I think the answer is no.
Slow.
Could you ever have the situation where you have, with the reduced density matrix for A takes this form 1 over n times the identity, but the reduced density matrix for B doesn't take that?
The answer is yes, but only in the following sense. If the B subsystem, for example, were bigger than the A subsystem, if they're the same size, no. Then if A takes the unit form, then B will take the unit form. What can happen is that B is bigger than A. If B is bigger than A, then what you might find for what you will find for the density matrix of B is that it has the same unit form in some block and then a bunch of zeros down here. Zero probability for B states down here, but the block here, which is of the same size as A, has the same kind of maximal entanglement. So the answer is yes, they can be different, but always in this sense. So it doesn't have to be zero, it could be other things down here. But at least if they're equal size systems, then if A is maximally entangled with B, then B is maximally entangled with A. And as I said, what it tells you is this remarkable fact that you can, if you're interested in what you would measure, if you measured some observable in B, then there exists an observable in A that you can measure that will tell you the answer you need. That's the notion of entanglement. Okay. And maximal entanglement is that. Let's do a couple of examples, a couple of simple examples, and I'm going to actually leave for you to calculate the density matrices for them. Yeah, I'll tell you what they are though. Yeah.
If the density matrix is a Hermitian matrix, can it be thought of as an observable with the same kind of status as position of momentum?
It could be. There are situations in which you could imagine the density matrix being equal to some observable. Yeah.
But in general, is it an observable estimation?
Well, not in. It might accidentally be equal to some observable that's known to you and that you might want to measure. But I wouldn't offhand say that the status of the density matrix is the same as a fixed known observable. Would you, Shelley?
I wouldn't say it is.
Yeah.
You could get yourself really confused if
Yeah, I
you
think
go too far in that direction.
Right. I'll give you an example from classical physics. All observables in classical physics are functions of P and Q, if you know what I mean by P and Q. Okay. On the other hand, the probability distribution is also a function of P and Q. Would you say that the probability distribution was an observable? No, you would say it's the probability distribution, even though it has the same mathematical form of being a function of P and Q. But okay, that's,
So you could say that all observables are Hermitian, but that not all Hermitian matrices are observable.
say it as you like. Okay, I would answer further, but it would take a little too long. Let's not go there right now. But it's an important question, but I don't promise to answer all important questions. Okay, now, let's do one or two examples. The sort of, what should we call it, the standard example is two spins. Assume you know a little bit about spins. If we have one spin, the theory of one spin is it can either be up or down. Now when I say up or down, we've chosen a quantization axis. It could be the z-axis. And up or down means the spin is up or down along the z-axis. You can work in other bases. You can work in the x basis, the y basis, or bases anywhere in between. But the states up and down along the z-axis are a basis for a single half-spin particle. And state vectors are simply of a single particle, consist of a coefficient, I suppose it would be psi up times up, plus psi down times down. And we call these two numbers here wave functions, because they're not much, they don't have much in proper, they don't look very much like waves, they're just two numbers, two complex numbers. Let's count how many degrees of freedom there are in this construction. We're not getting to gravity, are we? Well, we are. Let's count how many states, how many physically distinct states there are. How many real numbers are there in psi up and psi down? Well, the answer is there are two complex numbers. Psi's are complex numbers. There are two complex numbers, and so that's four real numbers. On the other hand, we know that psi star psi up plus psi star psi down should equal 1. That's total probability 1. So we might as well remove 1 degree of freedom. And one more thing, the overall phase, the overall complex phase of psi up and psi down don't count. They're not important in any physical quantity. Therefore, that removes another degree of freedom, and the number of degrees of freedom. By degrees of freedom now, I mean the number of physically distinct states, not orthogonal states, but physically distinct states, is characterized by two parameters. Those two parameters are actually nothing but the polarization direction of the spin thought of as a little magnet in space. Two angles. It takes two angles to describe a little vector, the orientation of a unit vector in space, and that's what they correspond to. But the main thing is there are two parameters describing the state. Now supposing we take the two-spin system, the system composed of two spins. What is the basis of states that we want to work with? Up, 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 down, down, up, and down, down. Let's think of the first entry as Alice's entry, the second entry as Bob's entry, in other words, A and B. Two spins, Alice and Bob both have spin, and these are the four possible states that you can have. How many independent parameters does it take to describe the state of the two-spin system? Well, you have to have an amplitude in front of each one of these. That means four complex numbers, adds up to 8. But again, you get to remove 2. The sums of the squares have to equal 1. And the overall phase doesn't count. So that brings it down to 6. You might have expected only 4. If a spin, a single spin, is characterized, the state of a single spin is characterized by two numbers, namely orientation on a sphere, you might have thought that the most general state for two spins is characterized by 4 numbers, namely 2 sets of angles. But the answer is 6. That simply means that there are more states, as expected, there are more states than just the product states. The additional states are the entangled states. Okay, let's think about some density matrices. Let's start with the product state. Start with product state. The product state looks like this. It could be alpha up, up, plus alpha down, down. Alphas are just complex numbers now, and these are the amplitudes. They called them psi before, but I want to now call them alpha. Sums of squares of alphas add up to 1. This times, meaning to say the second system, this is Alice's spin, and now Bob's spin. Let's call Bob's spin beta up, up, plus beta down, down. This is a product state in which Alice's spin is in the known state on the left, and Bob's spin is on the known state, in the known state on the right. We can calculate the density matrix for this. You can do it at home, but I'll tell you what the answer is. The density matrix is, it's a matrix, it's a 2 for Alice's spin. The density matrix for Alice's spin. It's a 2 by 2 matrix, and it's given by alpha star up, alpha up, alpha star down, alpha down. I think it's alpha star up, alpha down, star alpha up. And it may be that I should interchange these two, but just because I can never remember rows and columns very well. This is the density matrix. Notice that its trace is equal to 1. Oh, important thing. The density matrix of the alpha system doesn't depend on the betas at all. Of course it doesn't, because this is a product state, so things about the A subsystem shouldn't depend on the B subsystem. And in fact, we see that the density matrix for the A subsystem does not depend at all on the betas. What are the eigenvalues of this density matrix? And it's easy to figure them out. First of all, the sum of the eigenvalues is the trace. The trace is the sum of these two, and that adds up to 1. Alpha star alpha up plus alpha star alpha down is equal to 1. So, eigenvalues are P1 plus P2 equals 1. What about the product of the eigenvalues? You know a theorem about products of eigenvalues? I bet Shelley does. Come on, Shelley.
Determinant.
Right. The determinant of the matrix. Were you ever in one of my classes?
I think I was in one of your classes.
Did I pass you?
No, yes, I think
Okay.
you passed. You gave everybody an A.
I gave everybody. Okay, the determinant. Let's look at the determinant. The determinant is alpha star alpha up, alpha star alpha down, product of all 4 things, minus alpha star alpha times alpha star alpha, 0. Determinant is 0. This product is the same as this product, and therefore the product of the eigenvalues is 0. The only way this can be is if one of the eigenvalues is 0, and that tells you that the other eigenvalue has to be 1. So we see we're in exactly this situation that I told you before, that for the product state, there's one probability which is 1, and the other probability is 0. And in fact, if you ask, what is the eigenvector with probability 1, it's just the state here. Okay, so that's an example. This is an unentangled, boring product. As I said, you know everything about the alpha system, you know everything about the beta system, but measuring something in alpha tells you nothing about beta. Nothing about the B system. Let's go by contrast to a maximally entangled state. Now I'll pick one. There are many maximally entangled states. They're all related to each other in a particular simple way, but still, let's pick one. I'll pick one called the singlet state. Singlet. And don't ask what's a singlet. Don't worry about what's a singlet about. 1 over square root of 2 to normalize it. And then up, down, minus down, up. This is not a product, and neither Alice's spin nor Bob's spin is in a definite state. But there is a density matrix for each of them. And I'm going to write it down. This is a nice little exercise. Work it out yourselves. Work out the density matrix for Alice's spin. Okay? And you will find that the density matrix for Alice's spin is just equal to 1/2, 1, 1. In other words, it's proportional to the unit matrix. Being proportional to the unit matrix, the eigenvalues of each are 1/2. Equal probabilities for the two states up and down. That's what it means, equal probabilities. But it's interesting because the unit matrix is the same in every basis. If you were to go, instead of to the quantization along the z-axis, let's say a quantization along the x-axis, you would find exactly the same thing. That no knowledge, the state has no knowledge in it about the polarization or the probabilities, equal probabilities no matter what you measure. But, so this is one of these states which has minimal, basically zero information about either Alice's spin or Bob's spin, but there is some very important information in it. Namely, if Alice's spin is up, then Bob's spin is surely down. If Alice's spin is down, then Bob's spin is surely up. That's a very strong correlation. However, that correlation is even more pervasive if you were to rewrite the same state in the x basis instead of the sigma z basis. You would find exactly the same thing. You would find that if Alice measures sigma x in the plus direction, Bob will necessarily measure sigma x in the opposite direction. So this state has the property that there's no information about either subsystem by itself, but there's an enormous amount of correlation that whatever Bob measures, if Alice measures the same thing, you will get opposite answers. This and this, you get opposite answers. This and this, you get opposite answers. And so there's an enormous amount of quantum correlation between the two systems.
It's even more general. If one is circular, polarized one direction, the other one is circular, polarized.
Well, we're talking about half-spin systems now, but yeah, I mean, it's
Well, a half-spin system, you can also make
it's
combinations that are...
That's right. There are maximally entangled states of pairs of photons where the thing which is correlated are their polarizations. And the mathematics is identical. Right. So if you had a similar kind of state built out of photon polarizations, then if you measured Alice's photon, let's say the polarization along some axis, you would find that Bob's polarization was along the opposite axis, the perpendicular axis. If you measured instead circular polarization for Alice's photon, you would discover some value, plus or minus 1, and you would know that if you measured Bob's circular polarization, you would get the opposite answer, which I think is what you were pointing to. Am I right? Yeah, okay. So.
It's something which has
How
no
did Alice
classical
entangle?
analog.
If you want to get them maximally entangled, how did you get them entangled?
By letting them interact. You cannot get them to be entangled if they're separated and not in quantum interaction with each other. Now, this state is called a singlet state because it has angular momentum 0. So it's a singlet state. If you were to bring two spins together, and the spins and there was an energy that favored the singlet state, eventually the system would radiate a photon and do whatever it has to do to relax to the lowest energy state, and this could be the lowest energy state of a pair of spins. So there are many ways that you can, and there are many ways to get such things. It's not hard to imagine procedures, protocols for taking a pair of spins and putting them, starting them, let's say, in some unentangled state to create an entangled state. And most states are entangled. Most states are entangled, to some degree. This is maximally entangled, and that's, all right, I think, how far am I supposed to go? Am I supposed to put that?
Yeah, maybe a couple minutes to the conclusion.
All right, so let me say one or more two things. Next time, we will take up black holes, real black holes, and ask what this has to do with black holes. But before I do that, I want to talk about entropy. Yeah, give me enough time to talk about entropy a little bit. The technical definition of entropy, and this will take about 7 minutes. Okay, 7 minutes to do entropy. Everybody happy with that?
Mhm.
All right, entropy is a measure of ignorance. If you're talking about Alice's subsystem, the ignorance will be maximum in a maximally entangled state, because you know nothing about Alice's subsystem by itself. Entropy is a measure of ignorance. It's the opposite of knowing information. The more information you have, the less entropy you have, and vice versa. And it has a technical definition, which it was first discovered, I believe, by Boltzmann, rediscovered in a different context, in the context of simple, pure information theory, in the context of communication, you know, dots and dashes, bits, ups and downs, discovered by Claude Shannon, I think around the 1940s sometime. Boltzmann, of course, was 1890 or whenever it was. Shannon was, and then the quantum version of it, I suspect, was due to von Neumann.
Probably what you're ascribing to Boltzmann, though, should be ascribed to Gibbs.
Oh, well, was Boltzmann before Gibson?
Boltzmann was before, and he had a similar formula, but the meaning was a little different.
Okay.
I think you're talking about...
P log P, though, I think appears.
Yeah, it appears there, but it was a different, sort of a somewhat different meaning. It was really Gibbs.
Okay, I'm happy with that. All right. So, they were both heroes.
Yeah.
They really were both heroes. So anyway, what does entropy have to do? Entropy is a property, it's not a property of a system. It's a property of a probability distribution. Supposing you have some variable I, which for simplicity takes on some discrete values, and you're given a probability distribution. Don't ask where it came from, some probability distribution, so that each one of these has a piece of I. The probability of the ith configuration. The sums of the probabilities are 1, they're all positive or 0, and the definition of the entropy, I'll tell you what the entropy is a rough measure of how many states are important under the probability distribution. It's a logarithm of the number of states that are important. So for example, here's a distribution where only a small number of states are important. Here's a distribution where a large number of states is important. A distribution in which you know exactly which one is present. That's one of the p's equal to 1 and all the other p's equal to 0. That's a situation of maximum knowledge. And one p is 1, the other p's are all 0. And in this case, you would say there's one and only one state that's important under the probability distribution here. Here's its technical definition, and I invite you to play with it. Try out for some distributions and see how it works. See that it really does capture the idea of the number of the states, or the logarithm of the number of states. But I'm going to write down this formal definition. And as I said, I invite you to play with it and understand it. It's the definition of the entropy S. This is the entropy S. And it's the information theoretic entropy. What it has to do with thermodynamics is a later story. S is equal to the summation over all the states with a minus sign of the probability of the ith state times the logarithm of the probability of the ith state. That's the formula that's due to Boltzmann, Gibbs, Shannon, and in a certain form also, I think, von Neumann, but in a different form. Okay. Let's just look at it for a moment. Supposing there's only one state which is important under the probability distribution. That means there's one p and only one p which is non-zero, and it is equal to 1. Then there's only one term here, and it's given by 1 times logarithm of 1, and logarithm of 1 is 0. So the entropy for a configuration of a known, maximally known situation, where one probability is non-zero and all the others are zero, the entropy is zero. That's as small as it can be. It's always positive, incidentally. You look at it, you might think it's negative. But the log of a number less than 1 is always negative. So this is always positive. All right, what's the opposite extreme? The opposite extreme is that you have a probability distribution which is no information and every single one of the probabilities is the same. And let's say 1 over n, where n is the number of possibilities. Then what do you get? Then you get minus. Now, there will be n terms. Each term will have the probability, 1 over n, times the logarithm of the probability, logarithm of 1 over n, but there will be n such terms to add up. So, we can forget this 1 over n, it just goes away. Logarithm of 1 over n is called logarithm of n, and so the answer is logarithm of n. This is the maximum entropy. Maximum confusion, you can't get a bigger number than that for any probability distribution. This is the maximally incoherent piece of probability distribution, and its entropy is logarithm of n. Yeah.
Since you mentioned Boltzmann's constant,
Yeah, that's right. Well, this entropy here is now in units of the information fields. It will be compared with the entropy of Colonel, who was a steam engineer. There would be a Boltzmann's constant in front of it. Of course, at Colonel's time, it was not known that there was an information theoretic, and it wasn't known about bits and so forth.
and presumably Boltzmann's constant wasn't known either.
And Boltzmann, I don't think, knew
Boltzmann-
Boltzmann's constant.
Planck introduced Boltzmann's constants.
Is that right?
Yeah.
But Boltzmann must have had some idea that...
The constant was, I think, introduced by Planck.
Good. In any case, this is the information theoretic, not the thermodynamic, which would differ only by a factor of Boltzmann's constant. So we're going to ignore Boltzmann's constant. But, all right, I think we're about finished, but the lesson for now is that entangled states are states of large entropy when you look at a subsystem. When you look at a subsystem, entangled states have large entropy, and maximally entangled states have maximal entropy. Yeah. What this has to do with black holes, we will come to.
Right. Just a question about what you said so far. Boltzmann thought that what he was doing was providing a microscopic interpretation of thermodynamics.
Yes.
So he must have thought it was a property of the system.
I think by the time he was finished, he understood that it was a property of probability distribution, but
I don't think so.
I don't think
You don't
so
think so?
either.
No,
No.
no.
okay, so I don't know. I don't know what that. Boltzmann did understand, I believe he understood, that the second law of thermodynamics was a different kind of law than other laws. It didn't say, I think he did understand that it did not say that entropy always increases.
Right.
I think he did understand that entropy almost always increases.
That's
Yeah.
fine. That's
Yeah,
quite
no.
another thing from denying that it's
Yeah.
a property of the system.
Yeah. Okay, I'm not a historian, so I'm terribly inclined to want to defend Boltzmann at all costs, because I had a picture of him in my office, and he looked like a sweet, kind man.
David is not criticizing Boltzmann.
Yeah,
okay,
there's part of the discussions we had last week
yeah,
were aimed in the direction of saying,
Yeah.
look, Boltzmann very much had an idea of the statistical entropy he was talking about
yeah,
as a property of an individual system. And moreover, this wasn't supposed to be just a historical point. The point was supposed to be that for the purposes of understanding statistical mechanics, especially if it's supposed to be an account of what leads to thermodynamics and so on, he was right to think about it that way.
Where's my sword? I want to fall upon it. I absolutely believe you, and you're the experts at this. I'm not a historian, and
No, neither am I. It's not supposed to be historical.
are you Albert? I can't see you.
Yeah.
Yeah, okay. You definitely know more than I do about it. Right. So, last point. When you come to quantum mechanics and you have a density matrix, remember the density matrix in some basis is just a diagonal matrix of probabilities. If you were to calculate the entropy associated with those probabilities, what you would be calculating would be minus trace. Trace means sum over the diagonal elements of the density matrix, the matrix whose entries in the diagonal basis of probabilities, times log of the density matrix. Now, log of a matrix is a weird concept, but it makes perfect sense anyway. And this is called the von Neumann entropy. Do I have that right?
Yep.
Would you call it von Neumann?
Yeah.
Okay. This is the von Neumann entropy. It is simply the Shannon, Boltzmann, Gibbs, and whoever else entropy, except for a quantum ensemble of states characterized by a density matrix. Notice that if the system is in a pure state, meaning in a product state, and you look at one half of it, the entropy is 0. Quantum uncertainties don't contribute to the entropy, only the uncertainties associated with entanglement or the uncertainties having to do with not knowing which state you're in. Okay, next time we will come to what this has to do with black holes, why black holes have entropy, why they have temperature, and how it's connected to entanglement. Yeah. I see.
Towards the beginning of the talk, we were talking about, I think I might put this out away from next time, talking about black holes. But you were saying that this Alice region and the Bob region, in some sense, the distance they were separated has to do with their entanglement.
Yes.
Do you stand on that at all?
Oh, yes. But, yes, we will certainly expand on that.
Okay.
This will be one of the main foci of the lectures. The connection between the way geometry holds itself together and the way entanglement is. And these are new ideas. These are ideas of the last 5-6 years, and they're prevalent in a very small group of people who grew to some extent out of the string theory community, the black hole community, the quantum black hole community. They're ideas which are sort of emerging now over the last 10 years, I would say.
Lenny, you talked about entanglement without ever mentioning who really brought it back up to interest, which was John Bell.
No.
John Bell should be credited with the person who revived the interest in the subject.
Absolutely.
And
But there was a lot of discussion of that last week,
killed
Michael.
Einstein's. Well, let me see. I think he's the one who killed Einstein's idea that somehow you could still have a hope to understand quantum mechanics with some hidden variables that represented the probability issues.
Yeah. I
Bell would not
completely
say
agree that Bell was the hero who resurrected the importance of entanglement. But whether it's fair to say that Einstein, I suspect Einstein knew that he wasn't going to be able to understand entanglement classically. I don't know. You maybe.
No, I don't. Einstein, well, classically I don't know, but Einstein thought that because of these correlations that quantum mechanics, there had to be pre-existing values for all these spin components and stuff like that. Einstein had no clue that that was wrong, but that's what Bell clearly showed was wrong.
Yeah, it's true that Bell really nailed it. I'm guessing that Einstein's real discomfort with it is I think somehow secretly he probably knew that that it was in conflict with his classical ideas, and that's why he hated it so much. But I don't know.
I don't
He,
think.
he,
They're dead. Be kind to me. Be kind to me.
I like Einstein.
one of the things that always disturbs me is in the literature is that people quote Einstein's so-called spooky entanglement
Okay, people get better.
because it occurs at large distances.
Yeah.
There's nothing spooky about it. What is spooky is the fact is that the entanglement occurs at a point in space-time, and what would be spooky is if you separate it, as you do when you do these experiments, if you separate it, and then the correlations would disappear. That would be truly spooky.
That would be good. That would be
That
good.
would be the
No,
spooky.
no, you're not doing justice to Bell there with that. It's like what
I'm not
Bell
doing
said.
justice.
It's like what Bell said about Bertelsmann. I mean, it's like, you know, the same example of Bertelsmann's socks. He said some people think that the strange thing here is that you could have correlations at a distance. He said misunderstanding could hardly be more complete. It's much more than that.
But I'll tell you what I find most remarkable about it is the fact that a quantum state can be such that you know all that there is that can possibly be known about the composite system, and then you know nothing about the individual pieces. That is truly non-classical.
Yeah.
Classically, if you know what a composite system, if you know every detail that can be known about a composite system, then you know every detail about its pieces. Here you have a situation where you know everything that can be known about the composite system, and nothing about the individual pieces. That is what really spooks me. Well, it doesn't spook me. It excites me. It enthuses me. It makes me say this is something interesting. Good. Okay.